Dr. Céline Gounder, and this is Epidemic. Today is Tuesday, June 9th. Over the past couple weeks, we've been digging deeper into how the immune system fights COVID. We've learned that when the body battles a virus, it creates soldiers designed to defeat it. Some of these soldiers include antibodies and T cells. When the immune system wins the battle, it remembers its opponent, and that often results in at least partial immunity to reinfection. There are all sorts of immune system soldiers. Researchers are studying each one's role to figure out how to develop diagnostic tests, treatments, and vaccines for COVID. And when it comes to antibodies, they may have a role to play in treating patients.
In any epidemic, people who go first and survive have in their blood the capacity to help others.
That capacity comes from antibodies. This week on Epidemic, we're discussing convalescent plasma as a treatment for COVID. That's the scientific term for the transfer of antibodies from a COVID survivor to a COVID patient. It's one of the oldest moves in modern medicine's playbook, and it's currently being used to treat patients diagnosed with COVID.
The discovery that people who recovered from an infectious disease had something in their blood that could protect others if it was transferred was made in 1891 in Germany. And that, in fact, led to the first Nobel Prize.
This is Arturo Casadevall, chair of the Department of Molecular Microbiology and Immunology at the Johns Hopkins Bloomberg School of Public Health.
The 1890s was a period of great excitement because doctors realized that if you could transfer serum from either an animal or person, although it was primarily done with animals, that you could transfer immunity. And that allowed doctors for the first time to treat such things as diphtheria, which was a major killer of children.
For the purposes of our discussion here, serum and plasma are basically the same thing. It's what's left after you remove red and white blood cells and platelets from the blood. In 2018, there was only one single case of diphtheria reported in all of the United States, but in the late 1800s, it was a common childhood disease.
Basically, the children get sick, they develop an infection in their throat, a membrane forms in the back of the throat, it becomes very tenacious, and the children's often asphyxiated in front of their parents. It was horrendous. The only way to save children was to do a tracheostomy if you could get to them in time.
This is pretty horrific, having to cut a hole into a child's throat so they could breathe. But this was the only thing doctors could do until they got an idea from an unlikely place: rabbits. See, doctors had been experimenting with what would happen if they took the blood serum from a rabbit that had recovered from diphtheria and gave it to another animal infected with the same disease. What they found blew them away. The serum was packed with antibodies against the diphtheria toxin, and those extra antibodies gave the other animal a boost to its immune system that helped it recover quickly from the disease. So then they tried it on a human.
The descriptions at the time are nothing short of miraculous. There is a description of a doctor in the early 20th century administering serum and watching as the membrane in the back of the throat went away. So you could imagine how this was perceived. This was the cutting-edge technology in medicine. It was the first time in the history of humanity, really, that doctors could really intervene and do something about an infectious disease.
This method is now known as convalescent plasma transfer. Doctors used it again in 1916 to quell an outbreak of polio. During the influenza outbreak of 1918, doctors at the U.S. Naval Hospital treated their sickest patients with convalescent serum. But these studies were small, and none were blinded, randomized, or placebo-controlled, the gold standard in research today.
It had a major boost in World War I. Why? Because many sera were developed for use against gas gangrene, for example. But it was here in the United States where Physicians really adopted this and carried out the first controlled trials of serum.
Those initial controlled trials were conducted at Bellevue Hospital, where Arturo later trained and where I work today.
They managed to carry out what at the time was highly innovative clinical research, in which they would use the serum in one ward and not in another. And then they will compare the mortality between the two. Many studies were done at Bellevue. Many were done in what was then other centers in the United States against pneumococcal pneumonia. And it was shown that if you could treat pneumococcal pneumonia with serum, that you drop the mortality by 50%.
At Bellevue, scientists determined that the treatment needed to be given at the first sign of a lung infection.
You had to treat early. You had to treat in the first 3 days. If you waited to the fourth day of symptoms, you did not see an effect.
But it couldn't just be any infection. Many bacteria and viruses can cause infection, and convalescent plasma only works if the patient has the exact same diagnosis as the donor had. In February, Arturo wrote an op-ed for the Wall Street Journal titled "How a Boy's Blood Stopped an Outbreak," about a measles case in 1934. A doctor at a boarding school recognized a potential measles outbreak and used convalescent plasma to stop it before it spread.
What the school doctor did was he had a kid who came down with severe measles. And he had 66 other kids who had not had measles. And they established that there was likely to have been a major exposure to the kids. So the question was what to do.
Statistically, if you did nothing, about a third of those kids would have come down with measles.
So what he did was he took the serum from the blood who recovered, and he used that serum, he gave it to the other kids who were susceptible. He didn't have enough serum to treat 66 kids. So he also had to get some serum from New York State.
In those days, state laboratories produced serum to be used as treatment for various illnesses. This still happens today. There are serums available to treat snake bites, for example.
And what he did was he showed that if you give small amounts, what do I mean by small amounts? About 5 to 10 milliliters, that the disease did not occur.
5 to 10 milliliters isn't much. Picture enough liquid to fill a teaspoon.
2 of the kids came down with measles, and the measles was very mild. So it was an example in which you could use convalescent serum intervening in a situation of great exposure and showed that you can stop an outbreak.
Despite this early success with pneumonia, measles, diphtheria, and other diseases, doctors moved away from convalescent plasma in the following decades. The first reason had to do with the risk of blood-borne disease infection associated with convalescent plasma transfusions. Hepatitis B was discovered in 1965. Prior to identifying it, it was known colloquially as Australian antigen because it first showed up when an American patient reacted negatively to the transfer of plasma from an Australian donor. Transferring convalescent plasma presented the risk of transferring this and other deadly blood-borne viruses. There were also cases of what became known as serum sickness, when patients had an allergic reaction to the animal serum transfers. Technology advanced too.
Serum was the way in which you were treated against many infectious diseases up till 1940. And it was also the birth of serum use also led to the birth of many of the pharmaceutical companies because they began to produce it industrially.
In creating antibody-based therapies for infections, pharmaceutical companies distill the plasma down further to just the antibodies.
There begins to be a new technology, the ability to make gamma globulin. So by the late 40s, you begin to have the first immune globulins. So gamma globulin is the antibody in convalescent plasma. When you take convalescent plasma, you take in the liquid. That includes things like antibody, albumin, and all the proteins that we have in the blood. You can take, however, the plasma and put it through a purification procedure such that you only have IgG.
The blood is purified down to include only IgG antibodies, also known as gamma globulin. These are the antibodies we generate as our immune system response to an infection matures.
And that is today, obviously, the preferred way of using it because it's standardized. They usually, IgG lots are made from about 10,000 plasma units. And they're made by pharmaceutical industry. They're made, the best conditions industrially. So clearly, if you have a gamma globulin available that has high potency and high activity and efficacy, it's a preferable reagent to plasma.
Once pharmaceutical companies started making gamma globulin, convalescent plasma transfers were all but abandoned. They were cruder, less pure, and riskier. It was also around this time that antibiotics were invented. Alexander Fleming, another Nobel Prize winner, first discovered penicillin in 1928, but it took another decade for scientists to figure out how to produce penicillin at scale. During World War II, penicillin was commonly used to treat soldiers with battlefield wound infections and pneumonia. And by the mid-1940s, it was also widely available to the general public.
Antibodies are abandoned for the treatment of bacterial diseases because they cannot compete with antibiotics.
Still, it didn't mean antibodies didn't hold benefits of their own.
And one of the great paradoxes is that when you look back at the data, when they used it together, they often got better results than if they used either. But it was almost considered not worth the trouble to keep doing it. And the second thing that remains unexplained to this day was that when you gave antibody, people who would respond got better right away. So with penicillin, for example, you needed a few days after pneumococcal pneumonia to begin to feel better. These people got better within hours, almost as if the antibody was mediating an antitoxic effect.
Researchers and doctors decided that the effort didn't match the reward. It was a lot easier to write a prescription for a pill than it was to give an infusion of immune globulin. Antibiotics won the day. But in the case of an acute outbreak of a new virus, one that pharmaceutical companies have yet to develop therapies and vaccines against, it can take a long time to develop and produce them, including gamma globulin.
The problem is, and this is the problem in COVID, is that if we waited for gamma globulin, it will take many, many months before it was available. Whereas convalescent plasma would allow you to treat people almost immediately.
In treating patients with COVID, doctors are reaching for what's available to them now, and that includes this old technique of treating patients with convalescent plasma, without that distillation process to make concentrated immune globulin. When Arturo wrote his Wall Street Journal op-ed, his goal was to make the case for convalescent plasma to treat COVID patients under what's called compassionate use. That's when a therapy is administered before there's proof it works. In his op-ed, it worked.
Within a month, we had FDA approval to use compassionate use. We had IRB's approval for a variety of uses. And between the very end of March and today, 17,000 patients have been treated.
Public health agencies have made a serious commitment to the effort.
And this COVID-19 convalescent plasma, termed CCP, has become a major initiative to identify and collect plasma from very large numbers of recovered patients in order to generate therapeutic plasma to infuse into sick patients.
This is Michael Bausch. Michael is the director of the Vitality Research Institute. He's been studying infectious diseases for more than 30 years. And when the pandemic hit, the NIH and CDC tasked Michael with leading major responses based on the blood donor population.
Well, in the United States, both the FDA and the blood organizations have really scaled up the production, the collection of convalescent plasma. The FDA has enabled the qualification of donors potentially as soon as 2 weeks after recovery. So as the blood organizations have begun to open up recruitment and eligibility, we have had thousands of units of convalescent plasma donated.
Each unit of donated plasma is enough to create 2 to 5 doses of therapeutic convalescent plasma, and Michael is overseeing the distribution of those doses. Some is being used to treat patients in research studies.
The applications vary, and there are both formal randomized clinical trials where patients are being enrolled and either given convalescent plasma from recovered patients or control plasma that does not have antibodies to COVID-19.
Some of the convalescent plasma is also being administered under compassionate use. outside of research studies, often as a last-ditch treatment.
But there's also very large, if you will, compassionate use INDs opened that allow for the transfusion of this plasma into patients ranging from critically ill patients on ventilators to patients who are sick but not yet in the ICU but in the hospital, all the way back to prophylactic treatment of people who are exposed but not yet infected. So there's applications that really span the spectrum from trying to prevent acquisition of infection through the probably most important application, which will be in people who have early onset of pneumonia but not yet in the ICU or on ventilators. But there is a fair bit of use now in patients with very severe end-stage lung disease on ventilators.
If you think you might have had COVID and want to donate convalescent plasma, it's easy enough to get antibody testing. In some states, you can walk into an urgent care clinic and be tested for free, even without insurance. In others, you can ask a primary care physician to write an order for the test.
It takes about an hour to provide a convalescent plasma donation.
The process is different from a classic blood donation, where usually a nurse inserts a needle into a donor's arm and extracts enough blood to fill a 500 milliliter bag. That's almost a pound of blood. Then it's off to a donation center to be processed.
In contrast, the convalescent plasma that's being procured from these donors, both for individual patient transfusion as well as for immunoglobulin production, is collected using a technology called apheresis. And these are instruments that essentially are continuous flow centrifuges that take blood out of the patient's arm via a single needle in one arm. And then the blood flows into this instrument, and that instrument spins the blood in a way that allows separation of the plasma, the fluid phase of the blood, from the cellular part of the blood, which includes the red blood cells, the platelets, and the white blood cells. And the instrument automatically reinfuses into the donor their red cells and platelets and white cells, and specifically harvests from the donor the plasma. And the plasma at the end of the procedure ends up in a bag, a plastic bag, that again typically contains anywhere from 400 milliliters of plasma to 1 liter of plasma.
Once the body has antibodies to a virus, it will continue making them, at least for a while. We're not yet sure for how long, but for now, the important thing to know is that if your plasma is approved for donation, you can start to donate often.
The apheresis technology that we use to collect the convalescent plasma has two advantages. One is that we can recover multiple doses of plasma from a single donation. But the other is that by returning the red cells and other cells to the donor at the time they donate, we're able to allow that donor to return every week and donate frequently.
Convalescent plasma transfers have been used in other infectious disease outbreaks. When administered to patients with SARS in Hong Kong, the small subset of patients who got it seemed to have a lower mortality rate. That wasn't a randomized clinical trial, and some patients were treated earlier than others, so it's hard to know what that really means. During the 2009 H1N1 influenza pandemic, a slightly better designed but still imperfect study showed that convalescent plasma might have cut mortality by more than half. Convalescent plasma definitely isn't what I'd call a sure bet. During the Ebola outbreak in 2014, for example, convalescent plasma didn't work. There's some debate about this. Doctors questioned if it was being administered too late, or if the plasma contained a high enough concentration of antibodies. Regardless, it was not an effective therapy. Here's Arturo Casadevall.
It's thought to be a last resort. So many physicians often wait until the patients are really sick to use it. But in reality, if you are thinking convalescent plasma, or any antibody therapy for that matter, the earlier you use it, the much more likely you're going to get a favorable result. And we have known this since the 1920s.
Last week, researchers in China published a randomized controlled study in the Journal of the American Medical Association looking at convalescent plasma for treatment of severe COVID disease. It wasn't a big study. They had to cut the study short because COVID transmission had been brought under control by the lockdowns. They didn't have enough patients to keep enrolling. So maybe they didn't have enough patients to pick up a difference in treatment. It's also possible, like Arturo says, convalescent plasma may only work if given early in the course of disease, not when somebody is already really sick. And that's what we're doing in clinical trials now. We're administering convalescent plasma when someone's first hospitalized. That's how I've treated some of my own patients at Bellevue Hospital. Will it prove beneficial? Anecdotally, the answer is maybe. More than 800 U.S. health facilities are now participating in convalescent plasma studies.
This is totally consistent with history. We know how antibody works. We know that this virus can be killed by antibody. We know that people make neutralizing antibody. So everything kind of fits in. But in reality, we need to reserve judgment. And we need to say we need the best data available.
While we await the results of these studies to better understand if convalescent plasma works, in which patients, and in what situations, public health officials, doctors, and scientists are encouraging people to be tested for COVID antibodies, and if they have them, to donate plasma, which might help people sick with COVID now. That message is definitely getting through. In New York City, the Orthodox community was hit particularly hard by COVID. Leaders mobilized to donate plasma. Within a few weeks, New York had so much plasma, it was sending it to other cities. National campaigns are also urging people to donate, and those donations serve a dual purpose.
It could be used as convalescent plasma to treat people who need it today, as well as it can be used to make gamma globulin.
Gamma globulin. That's the next phase of antibody-based therapies, the stage of development that comes after the actual transfer of convalescent plasma.
The gamma globulin preparations are going to take a few months, but once they are made, they promise to give physicians a lot of good options. For example, you could use it in prophylaxis. You could use it when you have a major exposure. And in a situation in which there is a case in a nursing home, well, maybe you can treat everyone in the nursing home.
We'll delve into that next phase of antibody therapies next week on Epidemic. But before we go, I'm going to answer a question from one of our listeners. This is Clinton Bowers in Shreveport, Louisiana.
I have controlled type 2 diabetes and hypertension. My in-laws are planning a family beach trip to Orange Beach, Alabama soon, and they want my husband and I to go with them. There would be 9 family members going on the trip from 4 different households in 2 states. I recently had a SARS-CoV-2 antibody test, and it came back negative. So far, we have all been healthy, and no one has any symptoms going into this trip. I don't want to offend my in-laws, and I do not want to keep my husband from spending time with his family. We are not able to get together all that often due to the distance between our homes. However, I'm concerned this may not be the best idea for any of us due to the risk of COVID. I also feel like if my husband goes, I might as well go too, because if he contracts COVID, he's going to bring it home to me. Should we go? And if we do go, what can we do to minimize the risk? Thank you so much.
Clinton, thanks so much for your question. I think many families are facing similar tough decisions right now. The fact that you're antibody negative means that you haven't been exposed and infected yet. As somebody who has high blood pressure and diabetes, you do fall into a higher risk group, even if you are relatively young. The more family you have coming in from multiple households and states, well, that drives up the risk too. We know that a large proportion of COVID is transmitted by people with minimal or no symptoms at all, so even if everyone seems healthy, they could still be carriers. One useful resource in assessing the risk where you live is the covidexitstrategy.org website. That's covidexitstrategy.org. You can look up how your state is doing in terms of cases, testing, and health system capacity. Very few states have hit all of these targets. And unfortunately, in your case, neither Louisiana nor Alabama has. I don't think it's a good idea for you to take this trip. That said, if your husband wanted to join his family on the trip, he could opt to quarantine for 14 days upon return. He'd have to find a way to do that outside your home, in a place where he wouldn't be at risk for being exposed to others. And while on the trip, he could minimize his exposure to others by driving alone rather than flying. He and other family members should wear face masks at all times, socialize as much as possible outdoors, wash hands frequently, and minimize contact with others outside the family. Clinton, I'm faced with a similar conundrum. I'm in New York City, and I have family in Texas, Arizona, California, and Washington. I haven't seen them since Christmas, and it's not clear when we'll be able to see them again safely. My father-in-law has Parkinson's disease and lives in an assisted living facility. He's been healthy so far, but they've had a few cases. My mom, too, is older. I have 2 young nieces, and I'm sad to miss out on seeing them at an age when they're growing and changing so quickly. The COVID pandemic has been really, really hard for so many families. Epidemic is brought to you by Just Human Productions. We're funded in part by listeners like you. We're powered and distributed by Simplecast. Today's episode was produced by Zach Dyer, Danielle Elliott, and me. Our music is by the Blue Dot Sessions. Our interns are Sonia Baradwa, Annabelle Chen, Claire Halverson, and Julie Levy. If you enjoy the show, please tell a friend about it today. And if you haven't already done so, leave us a review on Apple Podcasts. It helps more people find out about the show. You can learn more about this podcast, how to engage with us on social media, and how to support the podcast at epidemic.fm. That's epidemic.fm. Just Human Productions is a 501c3 nonprofit organization, so your donations to support our podcasts are tax-deductible. Go to epidemic.fm to make a donation. We release Epidemic twice a week on Tuesdays and Fridays, but producing a podcast costs money. We've got to pay our staff, so please make a donation to help us keep this going. And check out our sister podcast, American Diagnosis. You can find it wherever you listen to podcasts or at americandiagnosis.fm. On American Diagnosis, we cover some of the biggest public health challenges affecting the nation today. In Season 1, we covered youth and mental health. In Season 2, the opioid overdose crisis. And in Season 3, gun violence in America. I'm Dr. Céline Gounder. Thanks for listening to Epidemic.